Great. So, of course, thanks to the organizers for organizing what looks to be going to be a wonderful conference and for accepting my talk this week. So this is going to be about some work in progress, which is maybe keeps getting longer and longer, which is also now joint with Liu, also at the University of Toronto. So hopefully it'll be out soon, but maybe I shouldn't promise things. So maybe the goal of the talk is to convince you that the first thing in this title is some very interesting space to look at and has some very nice combinatorics. And then we'll also see the second and the third things along the way. Okay, so what are matroid Schubert varieties? Maybe some of you have heard something about them already, but let me start with matroid Schubert varieties over C. So it actually can be defined over any field. So we fix some finite dimensional vector space, and we also have some finite vector configuration living in the dual. So if you like, you should think of this as defining a hyperplane arrangement inside V, where the hyperplanes are simply the kernels of each of these alpha E's. Okay, then the matroid Schubert variety is a way to compactify the vector space V by embedding it inside a product of projective lines. And so the embedding just sends each, you take your vector V in the vector space, and you evaluate at each of these alpha E's, and then this gives you some vector inside P1 to the C, and then you take the closure. And so you get some points which maybe have infinite coordinates. So these are the extra points that you get in the closure. So before I give you some examples, the goal, it's a very big picture goal, is to understand the topology of this variety. And of course, the variety is defined combinatorially, so somehow we should be able to describe the topology in terms of the combinatorics of A, and in particular in terms of the matroidal combinatorics of A. So maybe slightly more concretely, people want to compute topological invariance of this space, and most notably, there have been certain applications. So you can use some fancy machinery and deduce some very well-celebrated combinatorial results. So in particular, there is this Dowling-Wilson top-heavy conjecture, this introduction of matroidal Cauchy-Nalushtik theory. These are all things that have come from studying the topology of this variety. But okay, so these are working over C, or maybe more generally over some algebraically closed field. So of course, a lot of these algebraic geometric machinery is using very heavily the fact that you work over some algebraically closed field. We're going to do some terrible thing, and we're going to work over R. So, okay, basically everything is the same, but now, firstly, the combinatorics is maybe no longer just matroidal combinatorics, but also oriented matroid combinatorics. So when you work over R, you have the extra sign data in your hyperplane arrangement. And now all this, okay, geometry is hard, but hopefully I can convince you that sort of when you work over R, actually these spaces are a little bit easier, or at least you can use more combinatorial and purely topological methods without having to resort to all of these big hammers like hard left shirts and all this Kähler package and so on. Okay, and I set these slides up in parallel. I'm sorry to say I do not have any results that parallel the Dowling-Wilson top-heavy conjecture or matroidal Cauchy-Nalushtik theory. But if you know something about oriented matroids and these sorts of things, maybe you should come talk to me and tell me about what I should put in this line. Okay, so examples, pictures. So first, we'll start with the simplest example. So our vector space will be one-dimensional, and we'll have one hyperplane, or one vector. And so the matroid Schubert variety is going to live inside just the projective line, because we have one hyperplane. So, okay, this is our vector space. So I guess this vertical line in the middle is maybe going to represent the zero of the vector space, or the single hyperplane. And so I'm also going to draw on this picture this alpha 1. And so this lives in a dual space, so I draw it a different color. You should really think of this as living in a different space, but for the sake of the picture, I'll put them on the same plane. And so it'll be in blue. You see at the top the V dual is also in blue. Okay, so how does the compactification work? So we embed it inside this P1, and then we take the closure. So how do we take the closure? Say you go to the positive infinity direction along this space, okay, and you get to infinity, right? So infinity will be a point in the closure. And also, if you go along in the negative direction along the space, you also get to infinity. So these are the same infinities, of course, because there's one infinity in P1. So actually, we can see that in this case, the real matroid Schubert variety is really the entire P1. And over R, this is topologically the same as the circle. Okay, slightly more complicated, not that much more. Work in 2 dimensions, but yes, and this time we also have the coordinate vectors. So same story as before. So again, we go horizontally along this x-axis, and we get a point at infinity. But also in the second coordinate, the point is 0, right? Because we're moving along this hyperplane where alpha 2 is 0, and so that's also preserved in the limit, right? Okay, so we get this point. And actually, if you do this same sort of limiting procedure, but you maybe translate up by some finite amount, actually you get an entire affine line's worth of points in the closure, right? And then, okay, you do the same thing vertically. Okay, you get another affine line's worth of points. And similarly, going in the negative directions as before. And now also, we can go to infinity along, both coordinates at the same time, and we get the all infinities point. Okay, so, it turns out, of course, these are all of the points in P1 squared. So, this really is the entire matroid Schubert variety, and topologically, it's the same as, the torus S1 cross S1. Okay, less trivial. Still 2-dimensional, but now we pick the braid arrangement, so I'm not going to write down explicitly what the coordinates of these things are. But now, we have a 2-dimensional vector space, but now it embeds inside a 3-dimensional product of lines. Okay, so again, draw the vector space. As before, we can sort of take the limits. So let me just explain one of these. So for example, if you go, again, horizontally, so this is if you take the limit, you'll get a point where alpha 3 is finite, but alpha 1 and alpha 2 both go to infinity. Actually, alpha 1 goes to positive infinity, and alpha 2 goes to negative infinity, but everything is the same infinity in P1. So you'll get points which are of the form infinity, infinity C, and similarly for all the other ones. And as before, okay, you get the all infinities point. But in particular, you don't get any points where you have exactly one infinite coordinate, right? Because there is some relation between the alpha i's, and it means that the coordinates also need to satisfy this relation. But if there were only one infinity and a coordinate, then you wouldn't be able to achieve such a point in the limit of something where the coordinates do satisfy that relation. So, and of course, this vertical line is the same as this vertical line. And this one is the same as this one, and similarly with B, and also all of these all infinities points are the same point. Okay, so this one, okay, if you like to abuse the notation a little bit and you say that, it's really the set of points in this product of P1 satisfying this equation, where you maybe have to be a little bit careful about what you mean when some of these points are infinity, but, so this is some way to describe this variety. And, okay. But topologically, it seems like there's a very suggestive picture that I drew here, right? So it looks like, I drew a hexagon and then made some identifications. And the fact is that this is actually true, more generally, for any essential real hyperplane arrangement. So, okay, maybe I'll define some of these things in more detail later, but the result is that the matroid Schubert variety, as a topological space with the analytic topology, is homeomorphic to the zonotope of the arrangement. So this is this Minkowski sum of line segments with some identification on the faces. So this definitely needs more explanation, which I'll give in a bit. So this is not quite coming out of completely nowhere, but so in this previous work of Bartoldi, Enriquez, Ettingoff, and Reins, so I think they were probably the first to consider this interesting space, or this interesting way of making some identification on the zonotope. But for them, they were only considering this for the type A bermudahedron. And more recently, in this work of Ilin, Kamnitzer, Lee, Krzyzewski, and Rybnikov, so they proved this theorem in a special case where the arrangement is a Weyl arrangement. So where our set of vectors is the set of positive roots for some root system. So I should, of course, mention that their method of proof is completely separate from ours. For them, they are doing lots of root system combinatorics. So one nice thing about what we do is that we really understand the essential structure of what's going on, that really the essential structure is the hyperplane arrangement or the oriented matroid structure. Okay. So if you do, oh, sorry, yes.
So you have polymorphism. Is there something geometric about it? Does it preserve like singularities of identification?
Yes, but it's very not geometric.
Okay.
I mean, I can talk more about this later, but it's very much, okay. Sorry? Oh, sorry, the question is, is this homomorphism geometric in any way? And the answer is not really, but yes. Okay, so if you want to stop paying attention right now and think about this example a bit more, so if we have some two-dimensional arrangement, then, okay, I didn't tell you what the zonotope is, but maybe you can believe me that this is a 2n-gon. And so we make this identification of the parallel faces and so on, and actually you end up with some orientable surface, or the orientable surface with 2 points identified, depending on sort of parity arguments. So I think this is a little bit hard to visualize, but if you think about it enough, or if you've got enough intuition about this sort of thing, then maybe it'll work for you. Okay. So I need to maybe explain in more detail what exactly the statement means, what exactly this zonotope is and the identification. So the zonotope is, it's this Minkowski sum of line segments, so it's convex. And in particular, we understand in some very complete way the face structure of this polytope. So some very classical result. The faces are in bijection with covectors. So let me tell you what a covector is if you look at this diagram at the bottom. So take some point in the ambient vector space. So let's say something here, for example. And so you can see that when you evaluate that point at alpha 1, alpha 2, alpha 3, all of the coordinates are positive. Right? So the covector corresponding to that point is this all positives sign vector. And for example, if you live on, say, this horizontal hyperplane, okay, let me go horizontally, then if you're a point on that hyperplane and you evaluate at alpha 1, on the positive half of this hyperplane, let me say maybe, if you evaluate at a point there, then alpha 1 will evaluate positively, alpha 2 will be negatively, and then alpha 3 will evaluate at 0. And so the covector is exactly this set of signs of evaluations here. Okay, so the set of covectors of A is simply the set of all possible sign vectors that you get in such a way as you vary over all points in your vector space. So I guess also here there is 0, 0, 0 at the origin, which I didn't write down for aesthetic reasons. And the bijection goes like this. You take your covector. So let me just give this example for this face. So this is alpha 1 minus alpha 2. So you get to this point here. And then you get the interval from plus alpha 3 to minus alpha 3. And that's exactly this entire face. And maybe this is enough for you to believe me that this is some way to get all of the faces of the zonotope. And so now one can see exactly what can be meant by making some identification of parallel faces, because you can observe that if you have two covectors where the set of all coordinates going to 0 is the same, then you see that the faces themselves are simply translated by some vector, and so they're really isometric and parallel, and so we make the identification of such faces. Okay. So now the statement makes sense. Okay, so let me not really prove anything for you. Okay, so there are more things on this slide. Okay. So from the previous slide, we understand what is the correct statement, what is the correct statement to conjecture, that somehow the real matrix Schubert variety should be homeomorphic to this some quotient of the zonotope. And so we're actually going to construct explicitly such a homeomorphism. But oh no, what to do? Topology is hard. So we go back to the definition. We say, OK, by definition, the matrix Schubert variety embeds inside the product of P1s. And then you remember that you understand what the product of P1s is topologically. It's exactly the cube with also the same parallel phases being identified. So of course, if you like, this product of P1s is exactly the matrix Schubert variety coming from the coordinate hyperplane arrangement. So in this way, you might also believe the statement, but you can just think about it. And now, so the zonotope is a Minkowski sum of line segments, but another way to think about it is that it's a projection from the cube. So really, once you draw all those other things, you think, oh, there's a very natural map to go here. OK. We don't actually have this map. This sucks. So this is not actually a well-defined map on the quotient. So it's well-defined on the cube, but it's not well-defined on the quotient, which is very sad. So instead, if you work on the open stratum, if you work on the interior, and so actually this is a commutative square if you just restrict to V inside of the matrix Schubert variety, and all of this goes through. So, OK, at least there's some map. So V is this vector space, so the matrix Schubert variety is the closure of V. OK.
Do you repeat for me what's the red problem?
It's not well-defined. It's not so what is the problem with the red? It's not well-defined as a map on the quotient. It's well-defined as a map from the cube to the zonotope, but it's not well-defined as a map on the quotient of the zonotope to the quotient of the cube to the quotient of the zonotope. OK. And then I omit all of the details, and you can read some of them in the extended abstract. But so this is not entirely trivial, but maybe not that hard either. You just need to play a little bit with sign vectors. And it somehow miraculously, at least to me, manages to work out.
So is it because the locus where that's not defined it doesn't actually meet the matrix Schubert?
Basically, yeah. You can, yeah. I mean, OK. Picture. OK, so this is the A2 example. You can see sort of like where the matrix Schubert variety intersects the cube. It's sort of, yeah, OK, I'm not sure I have that much time, so let me not talk too much about this picture, but somehow this was very illuminating for me, so I decided to put it in my slides. OK, so now it's very easy to compute the fundamental group of this space. Right? So we have some very nice cell complex, and it's even so nice that it only has one zero-dimensional cell. So one can read straight away the presentation of the fundamental group. It's maybe very ugly to actually write down some actual presentation, but it's generated by rank 1 stuff and has relations rank 2 stuff. So in this particular example, we have the hexagon. This is a rank 2 thing. And then the relation is, of course, you go around the boundary of the hexagon, and this is homotopic to the identity. OK, and this is the only relation. OK, let me keep going. And so I guess in the end, I will manage to get to virtual Weyl groups. OK, so maybe many of you know the symmetric group. Probably many of you know the symmetric group. Probably many of you also know the braid group. So if you're a topologist, maybe you like some variation of this called the virtual braid group. So yeah, there is a topological interpretation of this. I don't really want to get into it, mostly because I don't really understand it. But as a group, one can say that it's the free product of a copy of the symmetric group with a copy of the braid group. So here, when I write Sn, I mean the Sn is generated by S sub is, and the braid group is generated by sigma sub is, satisfying the usual relations. And there are some mixed relations telling you how the generators of the two components interact with each other. And OK, we're going to introduce some new terminology for this group. So you can think about this group where you take the virtual braid group, and instead you say, what if I put 2 copies of the symmetric group? But they're not the same. OK, so you still have these mixed relations saying that the generators from different components interact differently with each other. So in the literature, this is also a topological thing. People call maybe the flat braid group or flat virtual braid group or things like this, many other names, but I'm going to call it the virtual symmetric group. And so these groups of authors that I mentioned before, so some combination of them, they managed to show that the fundamental group, when your matroid Schubert variety comes from the braid arrangement, that this is the pure virtual symmetric group. So there's some obvious map from the virtual symmetric group to the symmetric group where you just send all the braid generators and the symmetric group generators to a symmetric group, the corresponding symmetric group generator. And so the kernel of that thing is the same as the fundamental group of the real matroid Schubert variety. And one can upgrade this to some sort of equivariant fundamental group and actually recover the entire virtual symmetric group. Okay. So, I mean, this is the type A thing. And so the final result, maybe some nice application of our work, is that we can recover a generalization of this result for Weyl arrangements. So in this case, we recover the pure virtual Weyl group as the fundamental group. And also equivariantly, we recover the entire virtual Weyl group. And so this is some, I guess, new group. So there's recently been some development by Bellangeri, Paris, and Thiel, where they defined some analog of the virtual braid group in all types. And so, but they didn't consider this quotient, which this virtual Weyl group. And it appears for us as the fundamental groups of our spaces. So hopefully this means that there is something more interesting to say about these groups in algebraic combinatorics maybe in the future. Okay, so thank you.
Thank you. Any questions? Elena.
All right. Great talk. Thank you. So kind of a naive question. You're working inside this ambient real torus. I mean, that has a very nice cohomology ring. It's like an exterior algebra. You have these real subvarieties. Do they have interesting classes?
I have to say I don't know the answer to this question. I'm very sorry. It's a very natural question, but I don't know.
Thank you very much.
Yes, thank you. Is VSN finite? This is the first time I'm seeing it.
No, it's not. It's very not finite.
Thanks.
Thank you for the talk. Can you give me some intuition as to where the second set of generators is coming from?
So intuition as to the second set of generators for So in the fundamental group, you mean? Or okay, so the way that the proof of this theorem goes is, if you're a group theorist and you like groups, and you like to compute presentations of groups, so you like to compute a presentation for this kernel, for this pure braid group, and we observe that it's exactly the same presentation we get from our complex. That's exactly it. So I mean, I should say it's not really easy to see the generators, the both sets of generators, because this is really the kernel of the, right? We're not looking at the entire virtual symmetric. I mean, in the fundamental group, we don't look at the entire virtual symmetric group. So, and the equivariant fundamental group, quite frankly, I don't visualize in any significant way at all. It's just a formal property. But so the answer to your question about intuition is probably no. Sorry. No question?
So I'm sorry if I missed it, but for a specific matroid, do you get recover a classical Schubert variety in this construction?
So the question is there any relation of this space to classical Schubert varieties? The answer is no. Probably. Yeah.
So what motivates this title?
So I think the terminology, some people here can definitely correct me if I'm wrong. The terminology is maybe, so there's some affine paving of this space, which is, I mean, maybe no point to, there's some affine paving, and also there is some if you look at intersection cohomology of these spaces over C, for example, then you get this analog of causality theory. I think this is maybe one of the motivations for the name, but maybe someone else can tell me if I'm totally wrong about this.
Okay, thank you very much again.